Good morning, children. Today we're going to start oxidation states of transitional elements. Now I have taken in this 3D series 3D series from Scandium to up to I have taken zinc. Up to zinc I have taken actually. So what are the different type of oxidation states that they are exhibiting? Scandium only +3. It does not show variable oxidation state. Titanium show +2, +3, +4. Vanadium show +2, +3, +4, +5. Chromium show +2, +3, +4, +6. Manganese will show highest number of oxidation states +2, +3, +4, +5, +6 and also what? +7. Iron show +2, +3, +4, +6. Cobalt show +2, +3, +4. Nickel show +2, +3, +4. Copper will show only +1 and +2. Zinc will show only +2. Here also it does not show variable oxidation state, and here also it does not show variable oxidation state actually. Now coming to this, why this number of oxidations are exhibiting, everything we discuss, isn't it, in the next slide, isn't it? Now if you observe here, three types of elements we're having. See here, these are the starting. Scandium is a starting element actually. Starting elements, isn't it? Copper and zinc are ending elements. Where manganese is what? Middle element. Now middle elements, they're exhibiting more number of oxidation states, and end they're exhibiting less number of oxidation states, and starting they are also exhibiting very less. That means starting and ending elements exhibiting less number of oxidation states, where in middle part they are exhibiting more number of oxidation states. This we discuss very simple. See, whenever if they are having middle in the oxidation state, middle, what happen? You take one example, manganese here. Manganese configuration is what actually 3d5 4s2. It has more number of unpaired electrons. It has what? Isn't it? More unpaired electrons. Isn't it? More greatest number of oxidation states because of more number of unpaired electrons here. Unpaired electrons. So it is exhibiting more oxidation states. Next, in the beginning series, starting in the beginning series, also they are getting very small number here. Very small number of electrons there are. See, scandium is having only 3d1 and 4s2, very less number of electrons. Less electrons, less oxidation state, isn't it? And after that, elements at the end, last elements, end of the series, most of the elements are actually paired electrons. At the end, if you observe here, see, copper actually take 3d10, 4s2, isn't it? So it is paired electrons, no unpaired, paired electron there. 4s1, sorry, it is a 4s1, copper 4s1, it is not 4, it is 1 only, 4s1. So there are number of paired electrons are very less because they are completely, number of unpaired electrons are very less, they are completely filled electrons. That is the reason what happened, less oxidation state. So at the end, most of the electrons are completely filled. At the middle, most of the electrons are unpaired electrons. At the beginning, very less number of electrons are available. So that is the reason we are going to get this type of oxidation states. Next, these are the different number of compounds with oxygen. You see, manganese exhibiting variety number of oxides. Because of what? It can exhibit more number of oxidation states, having what? More number of unpaired electrons. Next, with fluorine and with oxygen. For example, cobalt forming a bondings with fluorine, vanadium bonding with fluorine. So here stability depends upon lattice enthalpy and bond enthalpy. Whether this compound is stable or not can be explained by lattice energy or bond enthalpy. For example, for oxygen, that means what happened, this type of oxides here, you have seen many number of compounds. No, their stability depends upon what type of nature here, multiple bonds. That multiple bonds are actually d pi, p pi. This I will explain by taking one example here. So we'll take one example here. Yes, this example. See, manganese show highest oxidation state +7. With the fluorine, it can show +4. This as example actually I will take here. See, actually when you observe here, whenever manganese bonded with fluorine, manganese bonded with fluorine. So manganese is getting like this. Fluorine is. I have taken 4 fluorines here. Now here it can form only sigma bonds. There are pi bonds are actually here not present. Why fluorine does not form? Because it has 2p5 like this. There are 2 electrons. And here also paid electron, here unpaid. Now this can form only what? Sigma bond. So somewhat stable, not very more stable it is. Now if you observe here what happened, MnO4 minus. Now in the case of this one, it will exist like this. Mn double bond O, double bond O minus. Now this is a pi bond. Here also pi bond is there. Here also pi bond. Now why it is forming pi bond? You see oxygen, if you observe, configuration is 2s2, 2p4. 2s2 I am writing like this. 2 electrons here. 2p4, 1, 2. This is the 2p4. Now one will form sigma bond, one will form pi bond. This type of arrangement is not there here. Observe here. Only sigma bond. Here extra you are getting pi bond. So because of this pi bond, the pi bond is because here d orbital involves, here p orbital involves. Therefore here d pi. So extra stability is getting because of what? D pi, p pi, pi overlapping is there. Because of this is getting stability. But this type of thing is not observed in the case of M1, F4 here. So that is the reason. This is important for us. P pi, d pi bonds are the reason for the stability and showing what more number of oxidants by manganese. See, actually you see, for getting +7, we can't place 7 elements around the manganese. You can't place what happens, 7 elements around the manganese. That is impossible. Maximum we can arrange what, or 6 like that. 7 we can't arrange. But here with oxygen, with 4 only we are getting what? +7 oxidation state here. Again back to what, we'll take some questions here. This one. Why do transition elements show variable oxidation states? Question is what? Why these all transition elements are showing what? Variable. You see how many oxidation states are exhibiting. You see variable oxidation states. There are different number of oxidation states they are exhibiting here. The reason we can explain very simple here. The reason is what? You observe here. The configuration of transition elements will be Ns and N-1. So all the electrons will fill in this case. It will be Ns2 and this will be what? 1 to 10 electrons. So here, so as number of electrons are increasing in d orbital, it can lose more number of electrons. More availability of electrons, more tendency to lose electrons. When they lose electron, they will get oxidation state here. We will take one example with vanadium. We taken actually vanadium. I have taken vanadium, isn't it? Configuration will be 3d3 4s2. Now if you lose these electrons, we get vanadium +2 3d3 4s0. Again if you lose one more electron here, -1, what we get? Vanadium +3 3d2 again 4s0. Again lose one more electron here, we are going to get vanadium +2, isn't it? Sorry, +4. We get 3d1 4s. In this way what happens? We can lose any number of electrons like this here. So variable oxidation state is because of what? Ns and N-1d orbital electrons which are undergoing bond formation. Next, name a transition element which does not exhibit variable oxidation state. We'll take one example here, scandium. Scandium does not show. This is very, very important question. Very, very important. Scandium, why it does not show variable oxidation state? You see, again the table we see. Does see scandium is there here? Only exhibiting 1. You can't see anywhere. +1, +3, +4. If you observe, only +3 is available. Remaining oxidation state is not possible in the case of scandium. So it does not show variable oxidation state. Reason if you want. What should be the reason? See, scandium I have taken. 3d1 4s2. Now first of all, scandium +2. 3d1 4s0. This is possible. Again if you lose this electron, scandium +3 3d0 4s. Now before 3D, what is the configuration? It will have 2s2, 2p6, then we get 3d0 and 4s. Now this 2s2, 2p6, sorry, 3s2, 3p6 is what actually, this 3s2, 3p6 is what actually octet configuration. So this is what highly stable. This is stable. So because of stable configuration having scandium plus 3, that is 3s2, 3p6 octet configuration, this is unstable. 3D having one electron in the orbital like this is highly unstable. So here also it will lose this electron, will get 3s2, 3p6 configuration. So that is the reason what happened is does not show variable oxidation. Plus 2 is not possible because highly unstable. No, that is the reason. Next, this same thing we just now we discussed this one. Among titanium plus 2, plus 3, plus which one is stable? Same thing we can write here. Titanium 3d2, 4s2 configuration. Titanium plus 2 means we have to remove this electron, isn't it? We have to remove this electron. So what we get here? 3d2. Titanium plus 3 means minus 1 electron, isn't it? We get 3d1. Again minus 1 electron, we get 3d0. Now again we are going to get here 3d0, 4s0 means what actually? Again you are going to get 3s2, 3p6 configuration, which is octet configuration. Again it will be more stable actually. Give reason. Manganese plus, just now we discussed this one, completed. 3D series, which elements show maximum number of oxidation states from scandium to zinc? Scandium to zinc, which will show maximum number of oxidation states we see here. I will take what here? Chromium and also manganese. Chromium configuration will be 3d5, 4s1. Here it can 3d5 and 4s2. Now how many electrons we can lose here? Up to 7. So up to plus 7 it will get here. How many electrons we can lose here? 6 electrons, up to plus 6. So it has what? More number of electrons, so it will get more oxidation state. It is having less number of electrons. That means that more number of electrons in terms of unpaired. I am saying in terms of unpaired. Here also 5 unpaired and here also 5 unpaired. Here only 1 electron to lose, here 2 electrons to lose. Unpaired you have to consider in the 3D orbital. 3D must be unpaired, isn't it? That should be how to consider. Manganese plus 2 and Fe plus 2, if you consider these two, which is what? More stable towards plus 3 oxidation state here. See, I have taken manganese here, 3d5, 4s2. Here I am taking what? Iron, 3d6, 4s2. First of all, we see Fe plus 2, Mn plus 2. Mn plus 2 means 3d5, 4s0. Fe plus 2, 3d6, 4s2. Now if I want to write Fe plus 3, what I have to do? I have to remove electrons from where? This paired electron I have to remove, and this is not at all, no, this is not half-fill configuration. This is not half-fill configuration. But here I want to write Mn plus 3 now. I want to write Mn plus 3. Which electron I have to remove? 3d5. For writing Mn plus 3, I have to remove electron from 3d5. This electron I have to remove. If you remove this electron, half-fill configuration will be disturbed here. This is actually half-fill. This will be actually half-fill configuration. That is the reason what happened. We can't remove electron from the half-fill configuration. It's very difficult to remove the half-fill configuration actually, isn't it? So here in iron, is it having any half-fill configuration in the iron? In Fe plus 2 state? No. It is not having half-fill configuration. So removing electron from this is very easy here. Here. This electron we can easily, even though if we remove this one, we get half-fill configuration. After removing, get half-fill configuration. So what I am saying here, manganese plus 2 converting into plus 3, where this is from d5 to d4. So losing what here? Losing what here? Half-fill. So that is never possible actually. It's difficult. So this never exists. It exists but highly not less stable, not non-spontaneous it is. But in the case of iron, conversion of +2 to +3, here actually D6, this one is D5. D5 you are getting half fill configuration. So definitely it is a spontaneous. Readily takes D6 converting into D5, readily takes place. So Mn+2 is more stable than Fe+2 towards +3 oxidation state, isn't it? Next. Assign both O2 and F2 stabilize oxidation state of transition metal, but the ability of oxidation, this just now we discussed because of multiple bonds. Oxygen can form multiple bonds, so it is highly stable actually. Next, which metal exhibit +1 commonly? Most frequently it will show +1. What that element? You see copper. I have taken copper here. Copper configuration is what? 3d10 4s1. Now it can lose this electron, will get +1. Now from this what happened? 3d10, it is completely filled. So we need to provide more energy to remove this electron from this completely filled here. So it lose this one electron, exhibit +1 common oxidation, frequently oxidation state. How is the variability in oxidation state of the transition elements and non-transition element? You take what? Iron show +2, iron show +3, even iron shows something but +4, many number of oxidation states. But if you observe what happened, lead can show only 2, +2, +4. Or you take tin, +2 and what? +4. Actually these two are actually non-transition element. They are non-transition. This is a transition element. Transition exhibit variable oxidation states, but non-transition elements will exhibit very less number of, only the something what happen, availability number of oxygen. That too what happen, even number you are getting. What is the reason? Which group it is? 14th group element. Configuration will be NH2 NP2. If you lose this electron, we get +2. If you lose all electrons, we get +4. You see, tin +2 because of losing NP2 electrons. Tin +4 because of losing NH2 and NP2 electrons here. Similarly, same thing, lead and tin, same thing is have lead +2 because of losing NP2, lead +4 because of losing NH2 and NP2 here. So that is the reason actually +2 and +4 is available here. But in this case, you are having many number of unpaired electrons you are having. So each and every unpaired electron is losing. You are getting what different type of oxidation states actually. Next, D block elements exhibit more oxidation states when you compare with a block element. It's very simple actually. Whenever if you observe here n-1 d orbital, ns orbital, n-1 d ns, between these two less energy difference is there, very less energy difference is there. So because of less energy difference what happened, they can easily lose electrons. That is the reason actually. Which oxo metal anion is exhibiting both oxidation states and group number are equal? Now we'll take what example, chromium Cr2O7 -2. Now what is the oxidation state of chromium? How many chromiums are there? 2 chromium and 7 oxygens are there. Each oxygen carries -2. Overall charge is what actually? -2. Now chromium equal to what? +6. What is the group number here? 6th group it is, isn't it? It's the group number is what also? 6th only. Next, we'll take what? Manganese, MnO4-. What is the oxidation rate of manganese? Manganese +4. Each oxygen carries -2. Overall charge is what? This one, -1. Now manganese exhibiting what here? +1. Which group it is? 7th group here. So this what happened? These oxidation states are completed. Now what you have to do here? You take all these questions, whatever the questions I discussed here, all these questions you need to copy you in your notebook and you have to submit as a assignment under oxidation states.